Buffers are solutions that resist the change to pH. The particles that cause a change in pH are hydrogen ions and hydroxide ions. So for a buffer to work, it must have a particle that would react with added hydrogen or added hydroxide. In the case of the buffer, sulfurous acid and sodium bisulfite, these are the particles that are present. You would have the weak acid molecules, it stays as molecules because it's a weak acid, and the sodium and bisulfite ions would dissociate in the solution. And you would have those three particles. So if hydrogen ions were added, they would grab onto the bisulfite ions. Forming the sulfurous acid molecules, and therefore the hydrogen ions were not allowed to change the pH of the solution. They were not allowed to lower the pH. What about if hydroxide ions? Well, they would react with the weak acid molecules, forming water and the bisulfite ion. Therefore, the hydroxide ions were not allowed to raise the pH. And so we see that when we have all of these particles present in our buffer system, they will resist the change of pH. So let's look at a different buffer system. In this case, we're going to look at the buffer system sodium dihydrogen phosphate and sodium monohydrogen phosphate. So let's take a look at it first. So the sodium would be a spectator ion, and the dihydrogen phosphate would be in equilibrium with hydrogen ions and the monohydrogen phosphate. So the dihydrogen phosphate, which has a negative charge, would be the acid. It's a weak acid. And the monohydrogen phosphate would be our conjugate base. So, if we were to show the equilibrium, the Ka expression, over our acid, this would equal our Ka. If we rearrange this, because what we're asked to do here is to calculate the pH of a solution in which we have equal amounts of dihydrogen phosphate and monohydrogen phosphate. So we're going to rearrange the Ka expression and solve simply for the hydrogen ions, which you know, of course, are analogous to hydronium. We're just not showing the water for simplification. Now, it needs to be mentioned that we're really talking about salts that come from phosphoric acid. And so this is really what we call Ka2. Phosphoric acid, being a triprotic acid, has 3 Kas. This is the second one. So Ka2 times the ratio of our acid which in this case is dihydrogen phosphate, and monohydrogen phosphate on the bottom is our conjugate base. Well, we said that we had an equimolar mixture. So if they're equimolar, they would cancel out because there's the same number of moles. So if equimolar, if we have equimolar mixture of our conjugate acid and base, the hydrogen ion concentration will equal Ka. So the hydrogen ion concentration will equal 6.3 times 10 to the minus 8th. And that gives us a pH of 7.20. That's 2 sig figs. Well, what if we have a mixture in which the conjugate acid and base are not the same? So we're taking baby steps here, learning about buffers. Let's take this equation right here, this expression that we used up above, and let's bring that down. So the hydrogen ion concentration is going to be the Ka times my conjugate acid on top and conjugate base below. And the Ka equals 6.3 times 10 to the minus 8th. Now, my ratio, it says here, is going to be 5 milliliters of my weak acid and 25 milliliters of my conjugate base. So they're the same molarity. So the mole ratio is going to be the same as the volume ratio here. So that's going to be 5.0 milliliters on top and 25.0 milliliters on the bottom. And of course, multiplying by Ka, we get 1.26 times 10 to the minus 8th. So the pH, and again, this is a case where our ratio is not 1 to 1. The pH is equal to the negative log of 1.26 times 10 to the minus 8th. And we only have 2 sig figs when we round, so that's going to be 7.90. So that's our 2 sig figs, just like we have 2 sig figs there, just waited to round at the end. Okay, now you'll notice that this particular buffer is tending to have a pH between 7 and 8. What if we wanted a pH of 5? Well, we're going to see that this is not the best buffer to use for a pH of 5 because the hydrogen ion concentration is going to be vastly different from the Ka. So with a pH of 5, the hydrogen ion concentration is going to equal 1.0 times 10 to the minus 5th molar. So Ka, let's use our expression, hydrogen times our conjugate base, the monohydrogen phosphate ion, over our weak acid, the dihydrogen phosphate ion. All right, let's rearrange that. If we put Ka over the hydrogen ion concentration, that's going to equal HPO4 okay, Ka is 6.3 times 10 to the minus 8th. And the hydrogen ion concentration at pH 5 is 1.0 times 10 to the minus 5th. So instead of our ratio being like we had up here 1 to 1, or here 5 to 25, those are very easy ratios to mix. What we end up with when we want a pH of 5 is 0.0063 to 1. That's just not a feasible amount to mix. How do you mix those when they're so vastly different? So this would not be a good buffer system. The dihydrogen phosphate, monohydrogen phosphate would not be a good buffer system for a pH of 5. We'll talk more about that later. The last question I want to discuss in this video is, would HCl and KCl be a good buffer? And the answer is no, and here's why. Hydrogen chloride, hydrochloric acid, is a strong acid, and it completely ionizes the potassium and the chloride. So just any acid at any salt won't be a buffer. Let's see what happens if we were to add hydrogen ions. What would they react with in those three choices? Well, hydrogen is not going to react with chloride, not in any way. So this is not going to resist the change of adding hydrogen, and this is not a buffer. And there's no particle also to react with hydroxide. So no reaction. This is not a buffer.